So section 4.5, the iterative methods of computing eigenvalues. So we're going to focus on the eigenvalues and we're going to use iterative methods. So how it works? For example, we're going to start with this. We're going to start with initial vector. For example, here is our initial vector. Let's say this is x0. Then our next step, which is going to be x1, is going to be here. We're going to find an x1 here. Next step, we're going to find x2. Then we're going to find x3 and keep going until we go into the exact solution. That means we're going to approach from both sides to the exact solution. How this is work? We're already going to start with initial value with x0. And especially with this section, you can choose any initial value to approach to the exact eigenvalue. We're going to say this is our initial value. To find the first one, you're going to multiply the matrix A by x0. We're going to get x1. We're going to start from x0, and then we're going to get x1. Then to find x2, we're going to multiply the matrix A by x1. To find x2, we're going to approach to the exact solution. This is the exact solution. And we're going to keep going. We're going to find x3, which is equal A times x2, and keep going until xk equal A xk minus 1. That's how it's work with, and to find the approximate eigenvalue. Then we're just going to say dominate eigenvector of A. That means this one, we're going to approach to the dominate eigenvector here. So this one is going to approach to the dominate eigenvector. Then we're going to find the eigenvalue of A. And imagine we're going to work with 2 times 2 matrix. But what about if we're working with 10 times 10? It's going to be different. It's going to be hard to find the eigenvalue. So this one is going to be easier to find the eigenvalue by using this method. Now, the dominate eigenvector how are we going to find that? You're just going to say xk divided by the component, or let's say the large component of xk. The large of xk. Large component of xk. Then by dividing each component of the eigenvalue vector by the large, you're going to get the dominate eigenvector. The eigenvalue, I'm going to use this information. Now, how to find the eigenvalue is going to be xk. You're going to divide the dominant eigenvector by the vector, the previous one. And we're going to check when we do the first example to find the eigenvector. So the eigenvalue. We're going to do these by all these by doing the first example. We're gonna check how we're gonna find or use this iterative method. If you see here, they're telling you a matrix A given along with an iterate 5. That means they're gonna, here's our initial vector, it's x5. We have the matrix A, which is the first question, the matrix A equal 7, 2, -6, and 7, 4. Look into 7, 4, 5, -1, and x5 equal 6, 8, 9, 3, 1. Be careful, it's not a decimal. And a 3, 4, 3, 4, 4. So what's the first step I'm going to do? I'm going to find the next vector. I'm going to start with x, the initial. I'm going to find the next one. How are we going to find the x1? That's mean x5. We're going to find the next vector, which is x6. It's going to be a times x5. That's mean it's going to be, here is the a, times x5, which is 6, 8, 9, 3, 1, 3, 4, 3, 4, 4. And let's see how much is going to be the result. So here's the important thing here. You have to be careful when you do the multiplication. So there's going to be 7. I don't know if you can see this one. 7 times 6, 8, 9, 3, 1 plus 4 times 3, 4, 3, 4, 4 is going to be 6, 1, 9, 8, 93. Now let's multiply the second row with the second element here with the first column. So it's 5 times 6, 8, 9, 3, 1 plus I have to put parentheses here because I put parentheses, a plus -1 times 3, 4, 3, 4, 4 is going to be 121. 1, 2, 1. I did it right. 5 times 6, 8, 9, 3, 1. Oh, there's something wrong because 3, 1. And plus -1 times 3, 4, 3, 4, 4. Now it's going to be different. Yes, it makes sense now. So this is x6, which is a 3, 1, 0, 1, 3, 1, 1. Now, next step, what I'm going to do, I need to find the dominant eigenvector. How are we going to find the dominant eigenvector? By dividing xk, which is here's xk, by the large component of xk. So the first thing, the large component of this one, 1, 1, 1, we just need to see which one is bigger. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So this one is bigger. So I'm going to divide everything by the large component here, which is this number. So the dominant eigenvector is you can divide x6 divided by x5 by the last component of x6, which is 1, 2, 3. So 4, 5, 6, 3 million, which is 3. I add 1, 2, 3, 4, 5, 6. It's supposed to be 6. 11. I add extra 1 here. So the last component is 3, 1, 0, 3, 1, 1. Yeah, be careful here. So this is the dominate eigenvalue, which is 1, 2, 3, 619,000, 619,893, which is going to be equal. This one is 1, and we're just going to divide this number divide by this one. It's going to be 0.500. I'm going to keep the 1 here. So this one is the dominate eigenvector, and they're telling you use 3 decimal places accuracy. That's mean the last number is 0.05005. Here is the number is 5. 3 decimals, so it's going to be 501. So we're going to type here, first of all, x6, which is the number here, 619893. And the number here is 310311. And the dominate eigenvector is going to be 0. Because here is 1. So this one is going to be 0.5, 3 decimals, 501. Now the dominate eigenvalue. How are we going to find the dominate eigenvalue? We're going to divide the components of xk, which is x6, by the previous one, by x5. So the dominate eigenvalue is x6 divided by x5. So this one is going to be equal x6, which is these two value. That's mean is going to be 619893 and 310311. Everything is going to be divided by x5, which is this 68931, and the second is 34344, and the result is going to be, you can divide 619,893 divided by 68931 is going to be 8.9929. So 9929, so it's going to be 3. Because they ask you to write down accuracy like 3 decimal places accuracy. Okay. So next one, we're going to divide 310311, 310,311 divided by 34344 is going to be 0, 3, 5. Because the number here is going to be 3, so we're going to keep it like this. The dominant eigenvalue now, which is going to be, you see, the amount is super small amount between this one and this one. So you can tell your lambda is going to be 9. I'm going to plug in this one as a dominant eigenvalue 9.035, because we need to write down the dominant eigenvalue, but we can tell that means the exact eigenvalue is going to be 9. Let's check these. So if I use the characteristic polynomial on this one, we have the matrix A, and we're going to use exactly the previous thing. So our matrix A is 7, 4, 5, -1. That means to use the characteristic polynomial is the determinant of A minus lambda I is going to be equal 0. That means the determinant of the matrix A, which is 7, 4, 5, -1, minus lambda 0, 0, lambda, supposed to be equal 0. Then it's the determinant of 7 minus lambda and 4, 5, and -1 minus lambda equals 0. That means 7 minus lambda times -1 minus lambda minus 20 is going to be equal 0. Then this distribute is going to be 7 times -7 and minus 7 lambda plus lambda and plus lambda squared minus 20 is going to be equal 0. Combine, so it's going to be lambda squared -7 with the is going to be minus 6 lambda, and -7 minus 20 is going to be -27 equals 0. Now, if you factor this one, lambda and lambda, we're going to take 9 and 3 equals 0. We need to get -27 and -6. So here's negative. I'm going to put, if we put positive here, it's not going to work. Let's put positive on this side and negative here. So it's going to be 3 lambda, -9 lambda. That's means lambda equal -3 and lambda equal 9. So the dominant lambda here is the 9. That's what we have to type with the next part is just to check the characteristic polynomial, which is you're going to put lambda squared here, minus 6 lambda minus 27 equals 0. And the denominator eigenvalue is going to be lambda, which is the highest eigenvalue. You will see we're going to do the same thing with the next example. I need to check this one, why it keeps saying wrong. But I don't want to spend that time just to check this example because we have 5. Let's go to the next one. And we're going to do the same thing. Let's choose different matrices because this one is going to be exactly the same one. You're going to get the same one. So I'm going to choose different numbers. Let's check this one. A is equal. So I can't plug in the solutions. 2, 1, 1, 1. It's exactly like the same. And we have x5 equal 1, 4, 4 and 8, 9. So let's work exactly the same thing what we did. The first thing we're gonna find x6, which is the next vector, and which is equal a x5. That's mean x6 is going to be a is 2, 1, 1, 1, and you're gonna multiply by x5, which is 1, 4, 4, and 8, 9. Then the result for x to the power 6 is going to be 3, 7, 7, and here is 2, 3, 3. So this is x to the power 6. Now, next step, the dominate eigenvalue is, we're going to divide x to the power 6 by the large component. So x to the power 6, we're going to divide, this is the large component, by 3, 7, 7. That means we're going to divide 3, 7, 7, 2, 3, 3 by 3, 7, 7. And the result is going to be, here is 1, and here is 0.618. Then the dominate eigenvector so the dominant eigenvalue, because this is the eigenvector. Now the dominant eigenvalue is, we're going to divide x6 over x5. Which is equal x6, here is the vector x6, which is 3, 7, 7, 2, 3, 3, and everything is divided by 1 and 0.618. And the result is going to be 2.618 and 2.618. You see that the both are the same. So our lambda, the approximate one, is 2.618. The dominate eigenvalue, you can choose one of these, which is 2.618. If you check the second part by finding the exact eigenvalue, your solution 100%, you're gonna reach to the equations to find the exact solution for the lambda, and you can't factor it just by using a quadratic formula. That's why your solution is going to be 2.6. You can't say 3, you can't say 2. That means your exact solution, because we got 2.6, 2.6, that means our eigenvalue is exactly 2.6. So when you find the characteristic polynomial, like this one, the equations, you can't factor it just by using a quadratic formula. That's why your solution is going to be a point. So example 3, we're gonna find, first of all, we need to find the dominant eigenvector and round your answer to 3 decimal places, and then we're gonna find the dominant eigenvalue. So let's do step by step. The first thing we're going to find x, this is x5, that means this is our initial. So x6 is going to be, we're gonna type a times x5. That means x6 is going to be a, which is the matrix 3.5, and here's 2, and here's 2.5, and here's 2, so here's a 3. And everything times this vector, which is 1016.625, and here is 813.500. Then we're going to multiply to find x to the 6. So I'm going to multiply 3 times 3.5 times 1016.625 and the plus 2.5 times 813.500 is going to be 5591.9375. Let's check. I'm not gonna round the number until I write down the result. Maybe it's gonna accept it because that's the wrong thing I think happened with the previous example, the example 2 or example 1. And 2 times, the second row is going to be 2 times 1016.625 and the plus 3 times 18, sorry, 813.500 is going to be 4473.75. Then we're going to find the dominant eigenvector How? By dividing this x6 by the large amount here, which is this 5,591, and this is 4,000. So this is the component of x, which is 5591.9375. Let's check how much is going to be the eigenvector. This one divided by this one is going to be 1. Now 4, which is this number, is going to be divided by this one. 0.8 and how many zeros do we have? 3 zeros and 3. That's mean if you round it, you're just gonna write down 0.800. Let's type here and check. Let's say 0.8 before I find the dominant eigenvector. And here's right. So now the dominate what I put here. Eigenvalue is we're gonna divide x6 by x5. x6 by x5. So x6 divided by x5, which is equal x6, which is this vector, 5591.9375. And the other one is 4473.75. everything is divided by x5, which is this one, x5, 1016.625 and 813.500. That's mean I'm going to divide. I have all the whole numbers here. Okay, anyway. So I'm going to divide 5591.9375 divide by 1016.625. So it's going to be 5.5. 5.5, and here's 100. 49. You see the last here? 49. So 50, have to add 1 here. Let's type it like this. And let's divide the second one, which is 4473.75, and divide this one by 813.500. Is going to be 5.4. 123,499. Let's check this one. That's mean our eigenvalue is between 5.5 and 5.4. Let's say this is 499, which is almost 5.5. So the dominant eigenvalue is going to be 5.5001, but the exact eigenvalue is going to be 5.5. Let's check here. For example, 3, I'm going to say here is 5.501. Let's see how much I put here. It's supposed to be 0, 0. Let's check. Let's say 50. Yes, and they're not going to accept it. Yes. So 500, because I didn't round here. So just 500. Because the 3 decimals. 0, 0. So the exact now is going to be, if you work on the exact one, compare the approximation value with A with the actual dominant eigenvalue. The actual dominant eigenvalue 100% is going to be 5.5. If you do the characteristic polynomial, this one is going to be the actual eigenvalue 5.5. So also you're going to use the quadratic formula because you're going to get decimals, or you're going to get 5.5 like a fraction, and you have to simplify it. You're going to get 5.5. So here's the steps for the power method. Always, we're going to let x naught equal y naught. Then we're going to compute xk, which is a times yk minus 1. That's mean the previous y. Then we're going to let mk be the component of xk. The large component here is going to be the mk, the large absolute value. Then we're going to find the yk by 1 divided by mk times the xk. This is going to be the dominant eigenvector, and here is mk is going to be the dominant eigenvalue. Let's do an example, but I'm trying to give you different numbers because I think this one is going to be the same thing. So let's do, if we have the matrix A is 4, -3, and -3, 12. It's almost similar to this one. And we have x8, let's say x7. The example I have in the book is different than the one. X7 equal negative 4.335 and 13.002. So now they ask you to find, look what they ask you here, MK and YK. The first two components they ask you, MK and YK. How are we gonna find that? If you check here, they're saying MK is the component of XK. Now we need to find M7. That's mean the large component with the large absolute value. So this is going to be our MK. That's mean the first MK is going to be, I have negative 4 and 13. So this one is the large one, 13. The large that's mean M7 is going to be 13.002. Now we need to find Y7. Until now, I didn't go to the next step because I need to find Y7, which is going to be 1 over MK, M7 times X7, which is equal 1 over 13.002 times negative 4.335 and 13.002, which is equal this one divided by this one is going to be negative 0.333. And this one divided by this one is going to be 1. So this is Y7. Now I have Y7 and X7. I'm going to find X8, the next step. You can create table for this one, and we'll see with next example, we're going to create table. So how to find the X? A times YK minus 1. A times Y7. That's why I need to find Y7. That's mean X8 is going to be A, which is 4, negative 3, negative 13, 12 times Y7, which is negative 0.333 and 1. And the result is going to be negative 4.334, and here is going to be 13.000. This is X8. That's mean M8 is going to be the large number with the large absolute value, which is 13. So now we're going to find Y8 equal 1 over M8 times X8, which is equal 1 over 13 times X8, which is what we found here, negative 4.334, and here is 13.000. So Y8 is going to be negative 4, and this is 1, negative 4.335. The last one is going to be this one times this one is going to be, oh, wait a minute. This one times this one, that's mean This one is going to be negative 0.333. And 1 over 13 times is going to be 1. That's it for this example. We're going to do the same thing with the next example, but it's going to be longer than this one. So we're going to choose initial eigenvalue with xk. And how to find the eigenvalue? If you go back here, which is the large component of xk, the large component here is 1. So here is our eigenvalue 1. And x naught equal y naught. So our y naught is going to be also 1, 1, 1. Now, when k equal 1, the second, how are we going to find that? You're going to do exactly the same thing. How to find xk? To find xk, you have to multiply a times yk. That's me going to multiply this matrix times this one. So it's going to be you're going to multiply this matrix times 1, 1, 1. So the first row, 5 times 1, 1 times 1, and 6 times 1. So it's going to be 11, 17. And the second row, 0, 5, 0. So it's going to be 5. And the third one is going to be 1 times 1 plus 1 times 1 plus 5 times 1. So 1 plus 1 is going to be 2 plus 5 is going to be 7. So here is the first xk. Now, the second, now we need to find yk. How are we going to find yk? 1 over the eigenvalue here. The eigenvalue here is the dominant one, which is 17. That means the large one. Then we're going to multiply 1 over 17, which is 1 divided by 17, equal this number. This number, you're going to multiply by xk here. So you're going to multiply 1 over 17 times 17 is going to be 1. 1 over 17 times 5 is going to be 0.294. How many decimals? I ask you 2 decimal places accuracy. So 294. So 29. And the same number, which is 1 over 17 times 7 is going to be 0.41. Here is the second iteration. Now, when k equal 2, I'm going to do the same steps. K equal 2, what I'm going to do, how mk, I need to find the xk, which is multiply a times yk minus 1, the previous y. So to find this one, I have to multiply the previous yk minus 1 times a. So it's going to be 10 times 1. So that's why you have to be careful. 10 times 1 plus 1 times 0.29, 0.29, plus 6 times 0.41. The result is going to be 1275. This is the first element, 12.75. And the second element is going to be 0 times 1, 5 times 0.25, 5 times 0.29 is going to be 1.45. And the third element is going to be 0 times this one, that's it. Now we need to find the third row. 1 times 1 is going to be 1 plus 1 times 0.29 plus 5 times 0.41, 3.34. So this is the second xk. Now we need to find the dominant eigenvalue, which is the 12. So 12.75. That's mean I'm going to divide 1 divided by 12.75 is going to be, here's 1 over 12.75 times xk. So times this one. The first one is 1, because this is the dominant, multiplied by the same number, but the reciprocal for the same number is going to be 1. Now this number times 1.45 is going to be 0.1113. So 0.11. And this number times 3.34 is going to be 0.261. So 0.26. That's the second iteration. Let's keep going. 2 more iteration. We're not going to find, because we have to stop until the difference, apply the method until the digit in the second decimal places of the iteration stop. It's not going to change. So let's go. We're going to find the new xk at the third iteration. Let's check how we're going to find it. By multiplying a times this k. So let's do it here. It's going to be 10 times 1 plus 1 times this number, so plus 0.11 plus 6 times 0.26. It's going to be 1167. So check the difference between the dominant eigenvalue is between 12 now and 11. We're approaching to, I think, 11. Yeah, we approach to 11. And the second number is going to be 10. Sorry, 0 times this number, 5 times 0.55, 0.11 is going to be 0.55. And the third row times yk is going to be 1 plus 0.11 plus 5 times 0.26, 2.41. So the dominant eigenvalue now, it's 11.67. Check, we're approaching to 11. From 17, we go into 11. Now let's find yk, which is going to be 1 divided by 11.67 is going to be 0.08. Now multiply this one by this number. The first one is going to be 1. The second one is going to be this number times 0.55 is going to be 0.047, so it's going to be 5. And this number times 2.41, 0.21. We're done from this step. And let's check the next one, the fourth iteration. Almost. Now what we're gonna do, we're gonna find x4, which is a times y3. So it's going to be, here is a, so 10 times 1 plus 1 times 0.05 plus 6 times 0.21. 11.31. 11.31. And the next one is going to be, because these are zeros, so 5 times 0.05 is going to be 0.25. And the last one is going to be 1 times 1, so 1 plus 1 times 0.5. So it's going to be plus 0.05 plus 5 times 0.21. It's going to be 2.1. The dominant eigenvalue is going to be 11.31. Then we're going to find y sub k, y sub 4, which is 1 over 11.31. So 1 divided by 11.31 is going to be this number. And we're going to multiply this number by x4. So multiply by the first number is going to be 1. Multiply this number by 0.25 is going to be 0.02. And multiply 2.1 by 2.1 is going to be 0.18. So check the eigenvalue approach to 11 as an exact solution. And this one approach to 11 as an eigenvector. And the second element, because the eigenspace or eigenvector is supposed to be 4, 0, 1. So you have to keep going. But if you check, the dominant eigenvector is keep going, approaches to number 11. If you keep doing the iteration, you're going to keep going toward the 11. That's why the dominant eigenvector or the exact eigenvalue is going to be 11. So that's how we're going to do the steps of the power method.